The flight control system is comprised of the primary and the secondary flight control systems and their associated system components. The primary flight control system consists of the ailerons and the multifunction roll spoilers for roll axis control, the elevators for pitch axis control, and the rudder for yaw axis control. The secondary flight control system includes the horizontal stabilizer, flaps and slats, the multifunction spoilers, when used as speed brakes or ground spoilers, and dedicated ground spoilers. The flight control system employs hydraulic actuators to control the respective flight control surfaces. These are generally referred to as power control units, PCUs. The ailerons are driven by conventional control cables that run from each control wheel back to a pair of hydromechanical actuators, moving the control surfaces. The rudder, elevators, and roll spoilers, as well as all secondary flight control systems, including the horizontal stabilizer, flaps, and slats, ground spoilers and speed brakes, are controlled electronically using fly-by-wire FBW technology. Primary actuator control electronics, primary ACE, and/or flight control modules, FCM, are employed to operate the respective electrohydraulic or electromechanical actuators. The primary flight control electronics are generally comprised of two complementary parts: the primary ACE, primary actuator control electronics, and the FCM, flight control module. The primary ACE effectively replaces the control cables of a conventional aircraft. Its logic connects the control column directly to the respective control surface, providing direct analog control of the surface actuators. Each primary ACE independently controls two surface actuators, or PCUs. The flight control modules provide software-based assistance to the primary ACE. Pilot inputs through the control column are combined with the digital control inputs from the flight control module to allow for high-level functions. The flight control module connects the flight control system to other aircraft systems via the ASCB bus, also referred to as Avionics Standard Communications Bus. The flight control system electronics provide two basic modes of operation. In the normal mode, the FCM provides software-based airspeed gain schedules and control limits to the primary actuator control electronic, primary ACE, as well as high-level functions such as airspeed augmentation, angle off attack, elevator thrust compensation, rudder flight authority, and yaw damper turn coordination. For example, with increasing airspeed, surface movement will be reduced. In the direct mode, the flight control module is removed from the control loop, for example due to loss of airspeed data. Control limits default to values set by the hardware in the primary ACE, and high-level functions are not available. Trimming is accomplished by activating the trim switches on either pilot's control wheels for pitch trim and quick pitch trim disconnect, and the respective switches on the trim control panel located on the center pedestal for both yaw and roll trim. A backup pitch trim switch is located on the trim control panel. Pitch trim is provided by the movable horizontal stabilizer surface. The following flight controls position information is displayed to the pilots on the lower portion of the ICUS. Flap and slat position, speed brake position, aileron trim, rudder trim, and horizontal stabilizer trim position. The flight control system synoptic page displays position, status, and failure information of the primary flight controls, ailerons, rudder, elevator, and multifunction spoilers, and the ground spoilers.
The Actuator Control Electronics ACE module is the primary component in the flight control system. A total of 9 ACE units are installed. 2 primary ACEs in the forward electronics bay, 2 slat flap ACEs, SFACE, in the middle electronics bay, 1 spoiler ACE in the forward avionics bay, 2 spoiler ACEs in the middle electronics bay, 1 primary ACE, and 1 horizontal stabilizer ACE, HSACE, in the aft electronics bay. The 3 primary ACE units control the rudder and elevator surfaces. The 2 SFACE units control the slats and flaps. The 3 spoiler ACEs control the multifunction spoilers. And the HSACE unit controls the horizontal stabilizer. Each ACE unit contains 2 independent channels, providing the direct connection of the cockpit controls to the respective actuators, effectively replacing the cable mechanism of a conventional aircraft. For example, primary ACE-1 controls the left outboard elevator actuator through channel 1 and the upper rudder actuator through channel 2.
There are 4 identical flight control modules installed. Flight control modules 1 and 2 are located in the Modular Avionics Unit number 1, MAU-1, in the forward electronics bay, while flight control modules 3 and 4 are located in the Modular Avionics Unit number 3, in the center electronics bay. The flight control module provides the digital interface between the flight control system and the rest of the aircraft avionics systems, and is required for normal mode operation of the flight control system. The flight control module units are connected to the primary ACEs via the Controller Area Network Bus, providing digital inputs to the primary ACE, which are combined with pilot inputs. This is used to augment pilot inputs for different airspeeds, and provides other high-level functions such as angle of attack limiting to the primary ACE units. The flight control system communicates with other aircraft systems via the Avionics Standard Communication Bus. The Avionics Standard Communication Bus provides data exchange between all flight control modules and with other components of the avionics system. The following systems provide data to the flight control system. Smart probes and the air data application modules provide air data for various airspeed augmentation commands. Inertial reference system provides aircraft attitude and accelerations to the flight control modules used for angle of attack limiting function computation. The proximity sensor evaluation module provides weight on wheels and ground spoiler position data to the flight control modules. Brake control modules provide wheel speed signals used for ground spoiler deployment. The FADECs provide thrust lever angle, TLA, to the flight control modules used for elevator thrust compensation. and the automatic flight control system provides autopilot commands. Data is also shared on the avionics standard communication bus for the ICAS to display warnings, cautions, advisory messages, and system status, and provided to the central maintenance computer for system diagnostics.
In order to reduce latent faults in the flight control system, an electrical power-up built-in test, PBIT, is employed to ensure that the flight control system components remain capable of executing their functions. Electrical PBIT provides detection of out-of-tolerance conditions and failures in the FCMs, PACEs, spoiler ACEs, and SFACEs. PBIT is automatically performed during the electrical power-up to the flight control system. PBIT is executed without application of hydraulic power since, for safety reasons, control surface's motion is not desired when PBIT is in progress. The PBIT expires after 50 hours elapsed time for airplanes post-mod. Primus Epic Load 21.2. Once the PBIT is expired, Flight Control Bit Expired ICAS caution message is displayed on ground during K1 phase, before first engine started, remaining on ICAS until an electric and hydraulic built-in test be performed. If the message Flight Control Bit Expired is already displayed before engine start due to the hydraulic PBIT expired, the message will remain active after engine start even if the hydraulic PBIT is successful. Note, for airplanes post-mod, Primus Epic Load 17.5, Flight Control Test in Progress status message is presented while electrical PBIT is in progress.
The hydraulic PBIT provides functional tests of the flight control actuators, and is performed when all three hydraulic systems are pressurized and takes 1 minute to complete. The hydraulic PBIT will be interrupted if any flight control surface is moved while the test is running. PBIT remaining time readout. For airplanes post-mod Service Bulletin 170-310017, Primus Epic Load 17.5, or an equivalent modification factory incorporated, a digital remaining time readout displays the hours until the electrical and hydraulic PBIT expire. If the value of the PBIT remaining time readout is higher or equal to 5, the numbers will be displayed in green. Otherwise, the color will be cyan. Invalid data will be represented by 2 dashes in amber.
The elevator control system installation is a fly-by-wire electro-hydraulic control system, providing control around the aircraft pitch axis. The system is controlled either by the pilots moving the control column forward or backward, or by the autopilot, taking the place of the pilot input commands. The elevator control system moves the left and right elevator surfaces, which are attached to the horizontal stabilizer. Primary ACE and FCM control logic is used to control 2 hydraulic elevator actuators for each surface, operating in an active standby mode, with no mechanical connection between the control column and the elevator surfaces. 2 independent feel units provide artificial feel and centering to the control columns. The aircraft is trimmed around the pitch axis by repositioning the horizontal stabilizer, using the pitch trim switch on the control yoke or the backup pitch trim switch on the trim control panel in the cockpit. The elevator control system uses conventional control column assemblies to drive the fly-by-wire elevator control system. A total of 4 primary ACE channels are used to independently control each of the 4 PCUs, providing the analog elevator control functions implemented in the primary ACE channels, such as column shaping, to vary the control column to surface gearing as a function of flap slat position. 4 independent flight control module units, located in MAU 1 and 3, provide high-level system augmentation to the primary ACE channels, such as gain scheduling as a function of airspeed, elevator thrust compensation, and angle of attack limiting. The 2 control columns are connected via a disconnect mechanism located between the 2 torque tubes. In the event of a jam in one of the control columns, the disconnect mechanism can be actuated by pilots through the disconnect handle in the cockpit, providing continued operation of the system. Following a disconnection, the pilot of the non-jammed side retains pitch control by means of on-side elevator. The system will remain disconnected for the remainder of the flight, and ground maintenance is required to reset the system. The PCU pairs connected to each elevator surface operate in an active standby mode, resulting in one actuator being energized and actively controlling the surface, while the standby PCU acts as a hydraulic damper, also providing flutter protection. The active standby status of the PCUs is alternated by FCMs through the PCU units following the power-up on ground each day, or switched automatically when a failure is detected. During normal power-up on ground, the following indication may be shown. The left elevator will be controlled by the inboard PCU powered by Hydraulic System 2, and the right elevator will be controlled by the outboard PCU powered by Hydraulic System 3. During the next power-up, the PCU will be alternated, and the normal indication will show that the left elevator will be controlled by the outboard PCU powered by Hydraulic System 1, and the right elevator will be controlled by the inboard PCU powered by Hydraulic System 2. With the elevator control system operating in normal mode, the elevator is gain scheduled as a function of airspeed, reducing elevator movement with increasing airspeeds. The flight control module adds additional high-level functions to the pilot inputs, such as elevator thrust compensation and angle of attack limiting. In the event of loss of airspeed information, the flight control module is removed from the control loop, and the associated primary ACE reverts into direct mode, using a fixed gain to flap slat retracted and a different fixed gain to flap slat extended to ensure aircraft controllability. The flight control module functions like elevator thrust compensator and angle of attack limiting are then no longer available. The elevator thrust compensation function, ETC, helps to reduce the pilot workload by applying elevator commands to reduce the pitching moment produced by increasing or decreasing engine thrust. The elevator thrust compensation function is computed in the flight control module as a function of N1, Mach, and pressure altitude. Elevator command is limited to plus or minus 5 degrees and is applied proportional to the amount of engine thrust above or below the reference thrust setting. The command is sent to the primary ACE units and is then summed with the normal pilot input. If one or more sensors required to perform the elevator thrust compensation function fail, the function is no longer available, and the respective message will be displayed on the ICUS. Stall warning is provided by the Auto Flight Control System, AFCS, by activating the stick shaker motor on the control column. The flight control module provides stall protection by means of the angle of attack limiting function. Once the stick shaker is activated by the Auto Flight Control System, the angle of attack limiting function reduces control column authority in the nose-up direction gradually until the control column reaches the aft stop, thereby limiting the angle of attack. The flight control module computes an angle of attack limiting command using angle of attack data, control column position, and inertial feedback. The command is sent to the primary ACE units, where it is added to the normal pilot input. If one or more sensors required to perform the angle of attack limiting function fails, the function is no longer available, and the respective message will be displayed on the ICUS. A loss of the hydraulic supply to either one of the PCUs is immediately detected by the pressure sensor in the PCU, and control is automatically switched to the other PCU. A PCU failure will be detected by the primary ACE, resulting in the shutdown of a failed PCU. Control of the surface will be automatically transferred to the other PCU. If a jam in one of the elevator PCUs is detected, the respective elevator surface will remain fixed at the position where the jam occurred. The pilot will be able to control the aircraft using the remaining elevator. The horizontal stabilizer trim control system, as a part of the pitch axis control system, provides the installation for trimming the aircraft around the aircraft longitudinal axis. The system controls the movable horizontal stabilizer using the pilot, co-pilot, and backup trim switches for manual pitch trim, and a combination of inputs from the automatic flight control system and the flight control module units for autopilot trim and speed brake auto trim. Horizontal Stabilizer Actuator Control Electronics, HSACE, and one Horizontal Stabilizer Actuator, HSA, are used to move the control surface. In order to avoid a possible pitch trim runaway condition, manual pilot trim commands are limited to 3 seconds. Airspeed augmentation is performed within the HSACE to modify trim speed actuation of the horizontal stabilizer as a function of aircraft speed. The Horizontal Stabilizer Actuator Control Electronics, HSACE, is a dual-channel active standby system. During normal operation, one channel operates in the active mode, actually controlling the actuator, while the other is in standby. The flight control module alternates the active standby configuration of the channels following the first power-up each day. Channel 1 is powered by main DC Bus 1, while Channel 2 is powered by DC Essential Bus 2. If an error is detected, the monitor lane will stop the electrical motor, in effect shutting down the channel. As a result, the standby channel then becomes the active channel. The Horizontal Stabilizer Actuator is a single electrical-mechanical actuator. 2 DC motors drive the actuator in an active standby configuration, each of them able to drive the actuator with full performance. Stabilizer position is provided to the HSACE and is used for monitoring and ICUS indication, for example an RO warning to the crew for trim position outside the takeoff green band. The HSACE responds to all trim commands with the following priority: Backup trim command, Pilot trim command, Co-pilot trim command, and FCM trim command. The following trim inhibit commands are implemented in the horizontal stabilizer control system. Pushing the pilot's or co-pilot's quick disconnect switch on the control yoke will disable both horizontal stabilizer ACE channels as long as the switches remain depressed, thus disconnecting the autopilot and stopping any active trim command. Releasing the switch will activate the channel again. two pitch trim cutout switches are located on the trim control panel in the cockpit. Pressing the buttons will disable the respective horizontal stabilizer ACE channel, switching it off. The other channel will then become the active channel. In case of stick shaker activation, the HSACE is prevented from responding to any pitch-up trim commands by a stick shaker signal from the auto flight control system. In the event of a failure of the horizontal stabilizer trim system, the autopilot cannot be engaged, or, if already engaged, will disengage automatically. In the event of an electrical emergency, only the HSTA-2 is operational at low rate. A loss of airspeed data from the FCM also results in low-rate operation of the horizontal stabilizer, providing structural protection to the surface. Pressing one-half of the trim switches for more than 7 seconds will deactivate this switch automatically. In the event of either cockpit trim failure, the respective message will be displayed on the ICAS. The lateral control system installation includes both the conventional hydromechanical aileron control system and the fly-by-wire electro-hydraulic multifunction spoiler control system, providing roll axis control. The system is controlled either by the pilots, rotating the control wheel left or right, or by the autopilot. The aileron control system controls two aileron surfaces attached to the rear spar of the wings, while the multifunction spoiler control system drives 3 outboard pairs of spoiler surfaces to assist roll control. A feel and centering unit provides artificial feel, force feedback, to the cockpit control wheels. The aileron control system is trimmed manually by using the roll trim switch on the trim control panel located in the cockpit on the center pedestal. The trim system is operated via the rocker-type dual control switch on the trim control panel, commanding the actuator to move and repositioning the neutral field position of the aileron system. The actuator is equipped with a timer, limiting a single trim command to 3 seconds. A quick disconnect switch, located on the pilot and co-pilot control wheels, disables the roll trim actuator by interrupting DC power to the trim motor as long as the switches remain depressed. A potentiometer within the actuator provides position indication to the ICAS system. The system consists of 2 conventional control wheel assemblies for pilot and co-pilot, used to drive both the fly-by-wire roll spoilers and the aileron control system. 2 forward torque tubes are installed underneath the flight deck, 1 for each control wheel. 2 independent aft torque tubes are located on each side of the center fuselage. 2 sets of cables connected to the forward torque tubes provide the aileron commands to the aft torque tubes. The left set of cables runs along the bottom of the fuselage to provide separation through the rotor burst zone, terminating at the left aft torque tube, while the right set of cables runs beneath the cabin floor and terminates at the right aft torque tube. A second set of cables is attached to the aft torque tubes, terminating at the wing quadrants, which drives the input levers to the hydromechanical aileron actuators, or PCUs. Cockpit control transducers provide control wheel inputs to the multifunction spoiler control system.
The 2 halves of the aileron control system are connected via a disconnect mechanism located between the 2 forward torque tubes. and an override unit mounted to the right aft torque tube. In the event of a jam in one of the cable circuits, the disconnect mechanism can be actuated by the pilots by means of the disconnect handle in the cockpit, separating the two halves of the system. Following a disconnect, half of the system remains operational. If the jam occurs on the co-pilot's half of the system, the pilot retains control of the left aileron with normal artificial feel. If the jam occurs on the pilot's side, the co-pilot remains in command of the right aileron with artificial feel provided by a bungee system. Only one pair of multifunction spoilers will remain available after the disconnection. Following a disconnect, the system remains separated for the remainder of the flight, and ground maintenance is required to reset the disconnect unit.
Any single jam of the mechanical components of the system will leave half of the system operational. In case of a jam in either pilot's control wheel or the associated cable assembly, the pilot is able to control the aircraft using the non-jammed control wheel. By operating the wheel disconnect unit to separate the two halves of the system. In the event of a jammed PCU actuator, the respective aileron surface will be hydraulically locked at the current position, and the pilot will retain control of the remaining aileron and all the roll spoilers by means of the jam override device. The two PCUs driving one aileron surface are both hydraulically pressurized during normal operation, thus operating in an active-active mode. The left and right inboard PCUs are connected to hydraulic system 2, while the left and right outboard PCUs are connected to hydraulic system 3. In the event of a disconnect of one aileron PCU from the surface or wing structure, the other PCU attached to the surface will operate normally. The aileron surface will operate normally, but the force authority of the aileron surface will be halved. The aileron PCUs normally share air loads during flight, and if the flight control module detects a difference in load sharing from the two actuators per aileron surface, and the message aileron RH fail or aileron LH fail will be displayed on the upper right portion of the ICUS display in the cockpit. When the hydraulic supply to one actuator is lost, the unit operates as a damper, and the system continues to operate normally, with the remaining actuator driving the control surface. In the event of a loss of all hydraulic systems, both actuators will be in damping mode, and the aileron surface will remain in the aerodynamic trail position. The spoiler control system commands 5 symmetrical pair of spoiler panels, 3 pairs of multifunction spoilers located on the outboard wing section, and 2 pairs of dedicated ground spoilers located on the inboard wing section. The system provides roll control to augment roll inputs from the ailerons, in-flight speed brake control to increase aerodynamic drag, to reduce airspeed or increase rate of descent, and the system also provides automatic ground and multifunction spoiler deployment to increase wheel braking efficiency, and aerodynamic drag to reduce the stopping distance after touchdown. A speed brake lever assembly located on the center pedestal in the cockpit is used to command the speed brakes. There are 6 multifunction spoiler panels, 3 on each wing, numbered L3 to L5 and R3 to R5. The multifunction spoilers have 3 modes of operation: roll augmentation, as a part of the lateral control system, speed brake, and ground deployment. In the roll augmentation mode, the spoilers are deployed asymmetrically, as commanded by the pilot's and co-pilot's control wheels. In the speed brake mode, the spoilers are deployed symmetrically as a function of speed brake handle position to increase the aircraft descent rate. The multifunction spoilers are automatically deployed symmetrically as ground spoilers following landing in order to reduce the stopping distance of the aircraft. The inboard and middle panel pairs are supplied by Hydraulic System 1, while the two outboard panels are supplied by Hydraulic System 2. Operating in normal mode, the roll spoilers are also gain scheduled as a function of airspeed. A roll spoiler augmentation command, computed in the FCM, is added to the normal pilot input in order to modify the roll inputs for changes in airspeed or different flap settings. Generally, an increase in airspeed results in smaller panel deflections, while increasing the flap setting also reduces roll spoiler authority. In case of a failure of the flight control module, direct mode occurs automatically. If the failure occurs in only one FCM, then only the spoilers associated with that FCM change to direct mode. Those two MFS panels will not deploy as speed brakes or ground spoilers, but will continue to operate in direct mode as roll spoilers with a fixed gain. If one flight control module changes to direct mode, the rest of the spoiler system does not necessarily change to direct mode. The speed brake lever is mounted in the cockpit on the center pedestal and is operated manually by either pilot. When the lever is in the fully forward position, the spoilers are in the stowed position. The lever latches into the stowed position when it is pushed to the forward stop, and must be lifted by the pilot to move it to the desired position.
The spoiler control system deploys the multifunction spoiler panels symmetrically as in-flight speed brakes. Moving the lever commands the system to deploy the multifunction spoiler panels proportionally as a function of lever position, up to the in-flight limit of 30 degrees. The speed brake will retract automatically upon selection of flap 2 or advancing the thrust lever beyond thrust lever angle, TLA, 70 degrees. In the event of a disagreement of lever position with actual surface position after automatic retraction, the advisory message, Speed Brake Lever Disagree, will be displayed on the ICAS. Note, speed breaker will automatically retract if IAS becomes lower than 180 knots.
The flight control module incorporates software to combine the roll spoiler commands and the speed brake commands into a composite command when turns are flown with speed brakes deployed. During right turns with speed brakes deployed, the left wing spoilers will retract partially as the right wing spoilers extend. Conversely, during left turns with speed brakes deployed, the right wing spoilers will retract partially as the left wing spoilers extend. The dedicated ground spoiler control system consists of 4 ground spoiler panels, 2 on each wing, numbered L1, L2, and R1, R2. The ground spoilers are used to reduce the stopping distance of the aircraft. The outboard spoiler pair is supplied by Hydraulic System 1, and the inboard pair by Hydraulic System 2. The panels are held either in the fully stowed position or fully deployed position, 60 degrees. Proximity sensors are installed near the actuator, and when the panel is opened 6 degrees or more, it will indicate a not stowed condition. The signal is used for takeoff configuration warning and failure indication on the ICAS.
After touchdown, The FCM units will automatically command all multifunction spoiler and ground spoiler surfaces to the fully extend position in order to increase wheel brake efficiency by reducing aerodynamic lift. Note: a white ground spoiler indication displays after airplane touchdown and when one of the ground spoiler panels open. The following spoiler logic conditions must be met: weight on wheels on ground, thrust lever angle below 26 degrees and wheel speed input above 45 knots, or airspeed above 60 knots. Following the rollout, the spoilers will automatically retract when wheel speed is below 45 knots for at least 5 seconds. If the throttle levers are moved beyond 35 degrees thrust lever angle after landing, the spoiler panels will automatically retract.
The rudder control system is a fly-by-wire electro-hydraulic control system providing control around the aircraft yaw axis. The system is controlled by the pilots. FCM high-level functions, and additionally, for airplanes equipped with autoland, the autopilot. The rudder control system moves a single rudder surface attached to the vertical stabilizer. PACE and FCM control logic is used to control two rudder actuators, or PCUs, operating in active and standby mode. With no mechanical connection between the rudder pedals and the rudder surface, a feel unit provides artificial feel and centering to the rudder pedals. The rudder control system is trimmed manually by using the yaw trim switch on the trim control panel.
The system uses conventional pedal assemblies to drive the fly-by-wire rudder control system. Two independent primary ACE modules drive the upper and lower PCUs, providing the analog rudder control functions implemented in the primary ACE, such as pedal shaping to vary the pedal-to-surface gearing as a function of pilot's input. 4 independent flight control module units, located in MAU 1 and 3, provide high-level system augmentation to the primary ACE units, such as yaw damping, turn coordination, and thrust asymmetry compensation, as well as gain scheduling as a function of airspeed. 2 electrohydraulic actuators, or PCUs, drive the rudder control surface. They are controlled by the associated primary ACE, commanding the PCU to drive the rudder surface. The 2 PCUs connected to the rudder surface operate in an active standby mode, resulting in one actuator being energized and actively controlling the surface, while the standby PCU acts as a hydraulic damper. The active standby status of the PCUs is alternated by the primary ACE units at the first power-up on ground each day, or automatically switched when a failure is detected. The upper PCU is powered by Hydraulic System 1, while the lower PCU is powered by Hydraulic System 3. In direct mode, the primary ACE units incorporate a fixed gain schedule to command the amount of rudder surface movement according to the pilot pedal input, producing 30 degrees of surface motion with full pedal input. With the rudder control system operating in normal mode, the flight control modules add further high-level functions to the pilot pedal inputs. With increasing airspeed, rudder gain is reduced by the flight control module in order to compensate for the increase in rudder effectiveness and providing structural protection to the rudder surface, vertical fin, and empennage. Gain schedule commands such as yaw damping and turn coordination are computed within the auto flight control system and sent to the flight control modules. Failures, such as an actuator runaway or a mechanical disconnect, will be detected by the primary ACE and the failed PCU will be shut down. Control of the surface will automatically be switched to the other PCU. In the event of a jam in the pilot's rudder pedal assemblies, the rudder remains active and will be actuated by high-level functions, yaw damping and turn coordination. In case of a jammed PCU actuator, the rudder will be hydraulically locked at the current position. The pilot will have sufficient control of the aircraft using the ailerons and the roll spoilers. The Embraer high-lift system consists of two actuation systems, one controlling 8 slat surfaces on the leading edge of the wing, 4 per wing, and the other one controlling 4 double-slotted flap surfaces on the trailing edge, 2 per wing. A single control lever, located on the center pedestal in the cockpit, is used to control the movement of slats and flaps. There are 7 slat-flap control lever positions, defining the combined positions of the slat and flap surfaces. Slat and flap motion is sequenced such that slats extend first, and flaps retract first when the motion command requires both surfaces to move. Deployment of both slat-flap surfaces is commanded by 2 slat-flap actuator control electronics, SF-ACE, and electrically operated using 2 power drive units, PDUs. The PDU consists of a gearbox and 2 electric motors. Each SF-ACE controls 1 flap and 1 slat electric motor. The slat-flap control lever in the cockpit allows pilot input to the slat-flap control system by converting angular displacement of the lever into electrical signals to the SF-ACE units. A light plate provides reference position markings for surface position selection. The slat-flap control lever has 7 positions, each having a detented arrangement as shown, resulting in the respective slat-flap surface positions and placarded speeds. Position 4 is gated in either direction for the go-around. For aircraft configuration logic, the position 4 is used only for takeoff and position 5 for landing, although the slat-flap 4 and 5 positions have the same surface deflection. During flap retraction phase, a flap retraction speed reference F is displayed on the airspeed tape to indicate the next flap selection. Transmission drive lines are installed on the leading and trailing edge of each wing, transmitting torque from the PDU output shaft to the actuators stationed along the wing, using torque shafts and angle gearboxes. The input shaft of each actuator is also a through shaft, transmitting the torque from actuator to actuator, maintaining synchronization within the system. A position sensor unit is located at each outboard end of the slat and flap drive lines, providing position feedback to the SF-ACE channels. The SF-ACE uses the information for closed-loop computing of the surface position, for detection of asymmetrical slat or flap deployment, and for surface position indication on the ICUS. A total of 4 flap actuators per side provide the actuation force to extend and retract the flap panels mounted on the trailing edge of each wing. The flap panels are double-slotted configuration, consisting of a main flap panel and an aft flap panel for both the inboard and outboard flaps. Movement of the main flap panel driven by actuators causes the aft flap panel to deploy relative to the main flap. Electronic skew sensors detect a disconnect in one flap actuator while the other on the same panel continues to operate. If differential movement of a panel exceeds acceptable limits, the slat flap ACEs will shut down the flap system, and the corresponding caution message will be displayed on the ICUS. There are a total of 8 slat actuators per side to provide the actuation force to 4 slat panels mounted on the leading edge of each wing. Electronic skew sensors prevent excessive panel skew in case of a disconnect in one actuator while the other actuator on the same panel continues to operate. If differential movement of a panel exceeds acceptable limits, the SF-ACEs will shut down the slat system, and the corresponding caution will be displayed on the ICUS. A single channel failure within the slat flap ACE or a single electric motor failure within a PDU results in low-rate speed operation of the flap-slat system. The advisory message, slat low rate or flap low rate, will be displayed on the ICUS. In the event of a double channel failure in the slat or flaps control system, the system will no longer be available. The caution flap fail and slat fail are displayed on the ICUS respectively. When the ram air turbine is the only source of electric power, the flap and slat channel power by AC bus 1 and 2 do not receive any electrical power, as only the AC essential bus is powered. This results in half-speed operation of the system. Additionally, when ram air turbine is the only source of electrical power, the slat flap ACE will prevent deployment of slats and flaps beyond position 3 to assure adequate airspeed for the ram air turbine.
The slats, flaps, and speed brake positions are displayed on the ICAS in both the analog and digital readouts. The pointers, in cyan, show the slat flap lever-commanded position. The flap scale represents the positions from 0 to 35 degrees, while the slat scale represents the positions from 0 and 25 degrees. Whenever the slat flap position information is invalid, the indication is removed from the display. The slat flap digital readout displays the slat flap selector lever position in green. In case of slat flap surface jamming, an additional box will be displayed in amber, as well as the readout. Whenever two boxes are displayed, the possible values are 0, 3, or full for the slats, and 0, 1, 2, 4, or full for the flaps based on the value of the surface angle. Speed brake selection is indicated in flight by a white speed brake annunciation and a white ground spoiler annunciation during the landing roll. Steep approach mode. The steep approach mode is a fly-by-wire function which allows the Embraer 170 to perform Cat 1 approaches with glide path angles up to 5.5 degrees. When the steep approach mode is engaged, the multifunction spoiler pairs 4 and 5 are partially deployed to 15 degrees for neutral control column to work as drag devices, increasing the sink rate with no change to the airspeed. Additionally, the horizontal stabilizer automatically compensates the airplane pitch during steep approach mode, engagement, and disengagement. The spoiler panel's deployment angle is modulated as a function of the control column displacement. Nose-up pitch commands reduce the spoiler's deployment angle, and nose-down pitch commands increase the spoiler's deployment angle. The stall speed, stall characteristics, the maximum lateral control, and the maneuvering capabilities for full flaps are unaffected by the steep approach mode.